Topic 7-3, perfect squares. This can be referenced all the way back in Chapter 1, talking about perfect squares, Section 5 on page 32. But also we're going to be dealing with expressions on Chapter 11, Section 6, starting on page 805. Alright, so this will be a chart that you can refer to, and we're looking at our perfect squares. So I went ahead and filled these in. So take a minute, pause the video, and fill in your values. But you really do need to know your perfect squares, at least, it says from 1 to 25. The ones that are often used, definitely 1 through 10, but to know some extras, 11, 12, sometimes 13, 15, 20, and maybe even 25. Those are probably the most important ones. So definitely knowing all of the ones from 1 to 10. So you might want to put a star by those. But knowing your perfect squares. So when I say a perfect square, you're saying the square root of 1 is 1. The square root of 4. So that would be like putting a square root sign around each of these numbers. The square root of 4 is 2. The square root of 9 is 3. So we have to know our square roots. So looking at the square root symbols means you're looking for perfect pairs. How many of the same number can I get from the square root of 25? That would be a pair of 5s. Sometimes doing this in a factor tree, get in the habit, it'll help you when we deal with variables in a little bit. For 169, if you do your factor tree, look up at your chart. That would be to a pair of 13s. So the answer is 13. Now be careful with this one because there's a negative. So you have a pair of 4s that is factored completely to a perfect square of 4, but you also want to say the opposite of the square root of 16. So it actually ends up being a negative 4. Here it has a 2 on the outside, so when you have your perfect pair of 12s, you've got to remember that once they're factored out, they're actually multiplied by what's on the outside of the radical. So your answer would be 24. Okay, let's look at a couple more on the back of this page. When there's one in a division sign, break it up. Sometimes it's helpful if it doesn't divide inside the radical, then break it up into 2 radicals, so that this is a perfect pair of 10, this is a perfect pair of 3, so your answer would be 10/3. This has a perfect pair of 9 and 9, but that 9 has to be multiplied by the 5 to get you 45. Over here, the square root of 1 and the square root of 36. That would be a 1, and this is a 6, but be real careful, you've got your opposite sign out here, so it's really minus. It's a negative 1/6. The same thing's going to happen over here. First, the square root of 1 and the square root of 4 gives you the 1/2, but you have to multiply this by a negative 2. So you actually end up with negative 1 for the answer to that one. Okay, I filled in every one of these, but not everything has a perfect square. Each of these cannot be factored. Well, no, that's not right. You actually can factor, but on this exercise, you're just looking for numbers that these square roots would lie in between. You can use the number line if you want to help you, or you can just flip it over to the other side of your chart and say, well, the square root of 81 and the square root of 100, this is going to be in between. In between. So that's how you look at each one of these. 2 is the square root of 4. 3 is the square root of 9. A 5 is going to lie in between 2 and 3. So that's what they're wanting you to fill in for these numbers here. Square root of 36 is 6. Square root of 49 is 7. So the square root of 44 would go in between. Square root of 9, square root of 16, so square root of 15 is in between. Square root of 36, square root of 49, we keep using that one, So the square root of 40 is in between number 6 and 7. Same thing with this one. Barely, I mean, it fits really close to the value of this one, close to value of 6, but it would be in between these two. And if you want to just check that with even a calculator, let's look at this one. We'll just do the last one. If I hit second square root of 38, you're going to get a decimal value close to 6.16. So that was that exercise of knowing where they lie in between. And that concludes 7-3.